This is Physics 1020 and 1090. It's the lecture for Monday, March 30th. We're starting chapter 27 on quantum physics. And in this video, we're going to be talking about blackbody radiation. But before we begin with that topic, I want to review or preview what is going to be going on in the rest of the semester in our class. We've talked about electricity and magnetism, and we've talked about optics. Our last big topic is going to be modern physics. Modern physics consists mostly of the physics that's been developed in the 20th century, a lot of the key ideas of relativity and quantum mechanics. Chapter 26 talks about special relativity. Unfortunately, we're going to skip chapter 26 because we lost that one lecture. You're welcome to take a look at it, but we won't be talking about relativity, and we'll be skipping chapter 26. So that means we're going to start with chapter 27, which is about quantum physics or quantum mechanics. We'll talk about chapter 27, then chapter 28 about atomic physics, really the ideas of Niels Bohr and Ernest Rutherford and how atoms are constructed. Then we'll go to chapter 29 on nuclear physics and study the nucleus of the atom. Finally, chapter 30 will be talking about nuclear energy, and we're only going to talk about the first 4 sections of chapter 30. Before we begin, though, I want to note that because of this historical development, it's a little bit of a different approach than we took for electricity and magnetism and optics, where we developed the basic science sort of from underlying principles. If you're interested in the history of modern science, modern physics, I recommend this book, The Making of the Atomic Bomb by Richard Rhodes. I've actually taught an entire honors college class based on this book. It's really a history of the Manhattan Project. One thing I want you to notice as we talk about the history of modern physics is how it parallels some of the political developments in the earliest 20th century. Basically, nuclear physics and atomic physics developed new sources of energy at the same time as fascism and Nazism was taking over in Germany and Italy. And those two ideas come together then with the Manhattan Project to build the atomic bomb in World War II. Keep an eye on these ideas. It gives you some insight into the impact of science on society. But I don't want to overwhelm you with history. So what we're going to do is we're going to limit the scientists that you need to know to these 8. Now, realize I could ask a question on the final exam about the history of modern physics, but it would be restricted to these 8 scientists. Let's go through them in alphabetical order. Niels Bohr. Niels Bohr is a Danish scientist from Denmark, and he's well known for the model of the hydrogen atom. That's something we're going to be discussing in chapter 28 on atomic physics. Then Marie Curie from Poland, although she worked mainly in France, she discovered radium and polonium, 2 radioactive elements, and she'll be very important in our discussion of chapter 29 on nuclear physics. Albert Einstein, German scientist, he studied the photoelectric effect that we'll talk about here in chapter 27, which has really established this idea that light has particle as well as wave behavior. He also was the founder of special relativity back in chapter 26, so he's going to obviously play a major role in the development of 20th century physics. Enrico Fermi, an Italian scientist, he did some of the earliest experiments in nuclear physics and is best known for us as designing the first fission nuclear reactor. And we will see his work and we'll talk about nuclear reactors in chapter 30 on nuclear energy. Werner Heisenberg, another German scientist, helped develop quantum mechanics. In particular, came up with the idea of the uncertainty principle, which we'll talk about not today, but probably on Wednesday. Lisa Meitner, an Austrian physicist, was the one who first realized how nuclear fission works. Nuclear fission, of course, is what underlies our nuclear reactors and the atomic bomb. So Lisa Meitner's role played a central role in the development of modern physics. Max Planck, we're going to talk about today, a German scientist who studied blackbody radiation and came up with Planck's constant. And finally, Ernest Rutherford, an English scientist. He discovered and explained radioactivity, so he'll be important in our nuclear physics chapter, but he also played a key role in developing the idea of the atomic atom. So he's going to also, we'll also discuss him in chapter 28 on atomic physics. So these 8 physicists, keep your eyes open for when we're talking about them, because you could be responsible for answering some simple questions about their role in modern physics. Okay, let's move on to blackbody radiation. The idea is that any object at some temperature, T, is going to give off radiation, electromagnetic radiation. And so the question is, what sort of radiation? Here's a plot of the intensity of the radiation as a function of the wavelength. So we all know the electromagnetic spectrum, the type of radiation varies with wavelength. If the object is only moderately hot, so temperature down here of 2000 Kelvin, that's still pretty hot. 2000, our body temperatures are around 310 Kelvin. So this is a hot object, but not extremely hot. Gives off radiation that peaks up here around 2 microns. 2 microns is going to be about into the infrared part of the spectrum. So objects of moderate temperature give off infrared radiation as their thermal radiation. And notice that it's very little at very short wavelengths, comes up at peaks, and then a fairly small amount at really long wavelengths. As you make the object hotter, so this black curve is 3000 degrees Kelvin. And a hotter object is going to, first of all, give off more radiation. Its intensity is higher. And second of all, its peak has moved down to a shorter wavelength, around 1 micron radiation. So it's still in the infrared, but it's a somewhat shorter wavelength of the infrared. And if you go up to 4000 degrees Kelvin, the intensity gets up even dramatically higher. Notice this is 2000 to 4000 in absolute temperature, but the amount of radiation given off is dramatically larger than that, larger than a factor of 2. And its peaks down here more like maybe 3/4 of a micron in radiation. It's even a lower wavelength peak. So this idea that the peak of the radiation emission happens at lower and lower wavelengths with higher and higher temperature is summarized in this what's known as Wien's displacement law. The maximum wavelength, the wavelength corresponding to the peak in the curve, times the temperature for that curve, absolute temperature, is equal to 0.0029 Kelvin meters. Now, I want to just remind you, you should have studied in your first semester of physics a little bit of thermodynamics. So we're going to be dealing primarily with absolute temperatures, and the scale for absolute temperatures is Kelvin. If you don't remember or haven't studied that, you may want to glance back at the thermodynamics chapter to remind yourself what a Kelvin temperature scale is. Let's see if this works. Well, if we want to figure out, say, what is the peak temperature for an object at a temperature 3000 Kelvin, we can solve this equation for lambda max, the peak wavelength, and we just dividing by temperature. We'll take 0.0029, that's this constant Kelvin meters, divided by 3000, and you'll get roughly 10 to the minus 6 meters. And 10 to the minus 6 meters is simply 1 micron. And that's about right. So this blackbody radiation Wien displacement law really lets us predict where the peak of the spectrum is of radiation given off by a hot object. Now, we saw that as you increase the temperature, you also get much more radiation given off. What we have here is a formula to give the total amount of radiation given off by a hot object. That is, you add up all the radiation given off at each wavelength, and you add it all up, and you get a total power, total amount of joules per second given off by an object at a certain temperature. And that's equal to, and if, by the way, Stefan's law is also discussed in chapter 11 on thermodynamics, in chapter 11, section 11.5.4, if you want to see some more about it. This total power is a constant called the Stefan-Boltzmann constant. And that is a fundamental constant of nature, which has a value down here of 5.7 times 10 to the minus 8. And it's going to have units of watts per meter squared Kelvin to the fourth. So you have Stefan Boltzmann constant times the area of the object. This is the surface area of the object, times, so that's meter squared, times the emissivity. That's a dimensionless number, really talking about how effectively an object can radiate heat. That is, an object can absorb energy. If it's a perfect absorber, absorbs all the energy on it, you'll have an emissivity of 1. An object that's a good absorber also is a good emitter. So an object that absorbs all the energy on it and then emits all the energy it can has an emissivity of 1, and we'll generally take objects to have an emissivity of 1. Something with E equals 1 is known as a blackbody. But objects can emit with less efficiency, and that would have a lower emissivity down to 0. Finally, you have your temperature to the fourth power. Now, being a temperature to the fourth means it depends dramatically on temperature. You double the temperature, you're going to not get a doubling, you're going to get 2 to the fourth, or 16 times the amount of power emitted. So the amount of power depends very sensitively on the temperature. So you have these quantities. So let's take a look and see a couple of examples of how you can appreciate the type of energy given off by a hot object. Well, before we do the examples, let me just point out that if you have an object that's at temperature T and it's surrounded or it's inside a room or a container that's at temperature T0, then you're going to have two effects happening. Object at temperature T is going to emit radiation, but you're also going to have the walls of this container emitting radiation, and it's going to be absorbed by this object. So what's the total net power emitted by this object? Well, Stefan Boltzmann constant, area, emissivity. Then you have a T to the fourth. That's from the amount of energy emitted by the hot object, minus T0 to the fourth. T0 is the temperature of the surroundings, and that's the amount that gets absorbed by this object. So if T is equal to T0, these will exactly cancel, and you'll be in an equilibrium where you have a net absorption or emission of any energy. But if T is not equal to T0, you can lose energy, or if you are a temperature less than the surroundings, gain energy from this process of radiation. Okay, first example is radiation given off by us, humans. We're going to start with our rule, the power, try to calculate the power given off by a human. Stefan Boltzmann constant times the area. Now, what's the area of a human? That's a difficult question because our skin, is very irregular. We're going to estimate that as about 1 cubic meter. It's probably a little more than that, but some areas are infolded and aren't as effective as emitting radiation. So this is a rough order of magnitude estimate for our surface area. We're going to take ourselves as a black body, emissivity of 1. Temperature of the fourth minus the temperature of the surroundings of the fourth. We'll take our temperature to be 310 Kelvin. Now remember, Kelvin to centigrade conversion is you take the Kelvin temperature and subtract 273. So 310 minus 273 gives you 37 centigrade. That's our body temperature, same as 98.6 Fahrenheit. The surroundings will take us roughly room temperature, which is about 290 degrees Kelvin. So if you take each of those to the fourth power, subtract them, multiply by the Stefan Boltzmann constant, you get about 120 watts is the energy that a human can dissipate through electromagnetic radiation. 120 watts is actually quite a bit. About our resting metabolism produces on the order of 100 watts. So we essentially have an ability to dissipate all our heat through radiation. Now, it turns out there are other mechanisms we can get rid of heat conduction, heat convection, but radiation is one very effective method of dissipating heat. Final example I want to talk about is trying to estimate or predict the temperature of the Earth. Have you ever wondered why the Earth has the temperature it does? Well, again, you have an equilibrium process. You have the sun producing a lot of light, a lot of energy, and that energy goes out into space. And here's the cold Earth with no energy source of its own, but it's sitting in sunlight, which warms it. Earth has a radius r. Now, how much sunlight hits the Earth? Well, at our distance, the distance we are from the sun, we receive 1,370 joules every second and every meter squared. So that's really known as the solar constant. 1370 watts per meter squared is the amount of energy striking the Earth. We're going to assume all that energy gets absorbed by the Earth, and that heats the Earth up. Now, why doesn't the Earth keep heating up and heating up and heating up? Well, as it gets hotter and hotter, it emits radiation by blackbody radiation. So we should be able to predict a equilibrium situation where the energy in through absorbing sunlight is equal to the energy out through emitting blackbody radiation. And we should be able to figure out roughly what the temperature is where those two are in equilibrium. So remember, this is the energy emitted by a black body. Stefan Boltzmann constant, area, emissivity will take us 1, temperature to the 4th. Okay, so we're going to set the energy absorbed, which is going to be the I, the energy from the sun, the intensity from the sun, watts per meter squared. And this is really going to be a power absorbed is power radiated. The power absorbed, you have to multiply that by the cross-sectional area. This would be the cross-sectional area of the Earth, just the cross-sectional area of the disk, of the circular disk that the Earth represents with respect to the sunlight, which would be pi r squared. That's the amount of energy that comes in and is absorbed by the Earth. How much energy does it give off by infrared blackbody radiation, Stefan Boltzmann constant, times the surface area of the Earth, and the surface area of a sphere is actually 4 pi r squared. So the difference between pi r squared, that's just the cross-sectional area of a cross-section of the Earth. This is the surface area of the entire Earth. The emissivity of 1, and that's the temperature of the Earth that we're trying to predict. So let's solve this. We see that the pi's cancel and the r squareds cancel. And what we're left with is t to the 4th is equal to e's 1. So you get the solar constant, I from the sun, intensity from the sun, divided by 4 times Stefan Boltzmann constant. Or taking the 4th power of each side, you get the temperatures, 4th root of I sun over 4 sigma. Put in the numbers we have for the solar constant and for Stefan Boltzmann's constant. Take the 4th root on your calculator, and what you get is 278 degrees Kelvin. Now remember, the conversion factor is Kelvin minus 273, so that's 5 degrees Celsius. It's not a bad prediction for the temperature of the Earth. This is an average temperature over both the parts of the Earth we live in and the North and South poles. So on average, that's pretty close. That's a rough prediction. There's a lot of things we don't take into account. We don't take into account clouds blocking some of the sunlight. We don't take into account greenhouse gases, which trap some of the heat into the Earth. But 5 degrees Celsius does give you an order of magnitude estimate just from the basic physics that we discussed today. So we've talked a little bit about blackbody radiation. Next class, or the next video, actually in this class, the next video, I want to delve into how Max Planck described this blackbody radiation and basically came up with the idea of quantization of light and into photons.